No, years before I'm actually.
What's
What's going on here?
You know,
Why did you laugh at me? You know what it was.
These windows go around.
Laugh at the joke and then. You always like laugh at the joke and then ask me.
Joe, what's your last name?
Shaven.
Spell it.
S-C-H-E-B as boy.
Wait, say it again. S-C-H-E.
E.
E.
I read a little bit of the ISON comment.
Yes.
It's going to be early in the morning.
Tell them
That's
about
what
the
they expect or whatever.
Can't spell.
Yeah, it'll be on the morning side.
Yeah.
Okay. What? What do you mean bummer?
Oh yeah, I was waiting on the floor to go see a comment.
No problem.
You probably won't find me.
I'll put a statement.
Is there something
Well, there I am.
something wrong with
Yeah, I'm on. Who's not on Facebook?
with the internet?
Alright, let's
I have
have
special settings. I don't like people to be able to search.
You want to start a pool to see when she's going to leave?
Facebook?
Our group.
Oh, the group.
Oh! No, that's the group chat. That's the group chat.
I'll start to throw up again.
No, just if that starts getting his zone, just leave the chat.
You're going to want to turn off notifications.
If that put in like 300 to 5,000.
Here we go.
All
Alright, here it is. That's the eclipse.
That's the moon, right?
No, well, that's the moon in front of the sun, yes.
That was great.
Coming up Sunday morning over New York City.
Oh,
That's
that's
awesome.
That's about what, I mean, I didn't have as nice a view of it, but you could see that much of it, yeah. So, ISON is supposed to be later this month, right?
She got some cute kids.
Wasn't there like a transit of Venus sometime last year?
Yeah.
Oh,
Was there?
I think so.
it's going he, right? It's okay.
Oh, that's a cool picture. Here are 3 of the moons of Jupiter. 1, 2, is that third one over here? And the shadows produced on the surface of the clouds, on the tops of the clouds. That is cool. APOD is cool. You really, if you're not looking at APOD, you should really. They're really some cool pictures. Ooh. Oh, this is. Oh, it's in Iceland. Ooh, that's really.
Iceland is such a weird place, honestly.
It is.
Yeah.
It has weird names and weird places.
A lot of volcanoes, right?
It does.
Yeah.
A lot of volcanoes I cannot pronounce.
Volcanic activity. Yes.
Everything that you can't pronounce.
Icelanders.
Okay, so we are pushing on through chapter 7 for the rotational motion. I have your tests almost ready, but I'm not ready to give them back, so I didn't bring them today, but I'm handing back other homework. So you have a worksheet on uniform circular motion. We'll also revisit the topic of uniform circular motion in between chapter 7 and 8 when we'll consider polar coordinates. And so we'll come back. We skipped polar coordinates in chapter 2 when we went through chapter 2 because we really don't use them until we get to chapter 8 or really maybe chapter 7. So I just postponed the topic. So we'll go back, read part of chapter 2 again on polar coordinates. And so when we're doing polar coordinates, we'll do uniform circular motion yet again, this time with a different coordinate system. Okay, so today you were supposed to examine the uniform circular motion in Cartesian form, and that's what I did in class for you on Friday. And so we ended that topic with the force on a body of mass m moving with a velocity v uniformly around a circuit, a circle of radius r. So here the speed is v. So the acceleration in this case is a vector pointing inward to the circle. And what's the magnitude of the acceleration in this case if I have those conditions?
It's opposite
Omega squared.
direction of.
Go ahead.
Omega squared r.
Omega squared r. Good. And in terms of the speed, it's v squared over r. So what's the relation between v and omega?
Omega.
Good. The speed is omega r. Okay. So what force is required to keep a body moving like this then? If it has that mass and that acceleration the force that's required must equal this. Now, this is not a force law. This is not a force law. It's not like Hooke's law, V equals minus K, F is minus Kx. It's not like that. It doesn't describe the force as a function of position. It simply says that in order to keep a body moving with that speed and that radius, that whatever force, God bless, whatever force exists must have that magnitude in order to keep a body moving in uniform circular motion. Right? Is that it? Do you understand what I mean? It's not a force law. So, for example, one of the force laws we had was the force due to kinetic friction is mu k times the normal force. Right? That's a force law. This is not a force law. This simply says that this is whatever force exists must have that magnitude. So there are lots of things. You could have a rope, and the tension in that rope would have to equal this if the rope is keeping that body moving. It could be gravity. In Chapter 8, we'll study planetary motion, in which case a planet that's orbiting the sun with a circle in a circular orbit, the force of gravity would have to have this magnitude. Okay? But the confusion here possibly is that there's an r in there and a velocity. You might think that this is somehow a force that has a dependence on velocity and distance or something. It's not like that. That's not what this means. Okay. So now the next thing we wanted to examine is a third measure of kinetic activity. So one of them was the momentum. A second was the kinetic energy. And now we introduce a third measure of kinetic activity called the angular momentum, which is going to be especially helpful in dealing with rotation. So let's consider first the momentum. It describes for us the translation of a body under the influence of impetus. The kinetic energy is another measure of the kinetic activity, but it has to do with, there's no direction associated with kinetic energy. So it's useful if we consider systems. If we have two bodies that each have linear momentum, then the total momentum of the system is something we could consider altogether. And this could be extended to more than one body. We have lots of bodies, and so the collection of the system has a total momentum, and so we're adding up all the individual momentum. In the same way, the total kinetic energy of a system can be considered, adding up the kinetic energies of all the participants, all the individual members of the system. So we saw an example where in a binary collision where we have two bodies coming towards each other, the total system may have no momentum. There may be no total momentum for the system, that is, it's zero. Yet there's something going on. And the kinetic energy is a way of describing this kind of motion, for example. The bodies coming towards each other or bouncing away from each other. So the kinetic energy was useful, a way of describing activity that's present in the system, which is not revealed by the total momentum. In the same way, the angular momentum is going to be another measure of the kinetic activity of the system, which will be especially useful when we're talking about rotation. So when we have a system where the bodies may be moving in kind of random directions, there may be no total angular momentum for the system, but there might be a kinetic energy. On the other hand, we might have a collective motion of all the bodies moving and rotating. And this is described for us nicely by this angular momentum. So the angular momentum provides yet another way of describing the motion, the kinetic activity of the body, with a special interest in rotation. Okay, so this is how it works then. If we have a single body and look at the angular momentum, so for the uniform circular motion, the angular momentum, r cross p, is a vector that comes out of the plane. And we can see here r cross p is going to be r cross m cross v, right? Or, I'm sorry, r cross mv. We can pull a factor of m out front here, m r cross v. And so for your homework problem, you should be able to demonstrate that this has a magnitude m omega squared r times z hat, where z hat comes out of the plane here. We set up in this problem early on a coordinate system x and y in order to deal with this. So z comes up out of the plane. So that describes a vector coming up out of the plane, and that vector is actually the same regardless of where this body is in its orbit. So it doesn't matter where this body is in its motion around the circle, this vector L, which is the cross product of R and P, points out of the board. In fact, L is a constant of the motion. L doesn't change, regardless of where it is in its orbit around that circle. And there was another vector that we were concerned with. Let's see, hold on. I've got this backwards here. It's only one omega and r squared. There we go. We defined another vector, remember omega, which describes the rate of rotation of this body. Is just omega, and now it's going to be perpendicular to the plane of the motion. So it's along the axis of rotation, which is, again, out of the board, out of the figure. So we could write then L is mr squared omega. And this combination of constants, mr squared, keeps cropping up, and we're going to call that I, big I, which is going to be called the moment of inertia. This is a combination of factors in the motion that keep coming up over and over again. And the significance of the moment of inertia will become clearer as we go through this. Okay. All right, so I have this relationship between L and omega, and you are to prove, generally speaking, that L, the angular momentum, describes an interesting aspect of the motion. And one way to investigate that is to take the time derivative to see what happens to L. So part of your homework was to demonstrate how to do the derivative of a cross product. And so you should have been able to demonstrate this. Okay, so what is then V cross V? Generally speaking, what is any vector, cross product of any vector with itself? Zero. Why?
If they're in the same direction.
Correct. So regardless of what way the velocity is pointing, this is going to be zero. Okay, so the time derivative of the angular momentum is going to be r cross the force that's acting, the net force acting on that body, right? So there could be a number of forces, and this is the net force. Using Newton's law, we can rewrite dp dt as the net force, or the sum of forces acting on the body. So I'll just write F, or I could be more explicit about it, the net force. So I could have a sum of forces acting on this body, in which case this would represent a set of terms. So I'm going to call this generally torque. Torque creates a change in the angular momentum if it's present, and each force that's acting on the body will produce a torque. So just like I had an equation of motion before, which was Newton's law, dp dt is equal to the sum of forces acting on a body. Right? This was Newton's second law. Now I have an equation which looks like the analog to that for rotational motion. The derivative of the angular momentum, which is a characteristic of its rotation, is going to be the sum of torques. If I have a set of forces acting on the body, each force produces a torque. Okay, what's the difference between Newton's second law and this new law that we have? Well, there really isn't any difference at all. There's really no new physics in this. We haven't really done anything except to re-describe it in a different way. So just as the kinetic energy didn't really introduce anything new in terms of momentum, it's just expressed the momentum in a different way, In the same way, the angular momentum is expressing the momentum in a different way that's well suited to characterizing rotational motion. But it's not really anything new. In fact, we derived this law, the LDT is sum of torques, we derived that from Newton's second law. Right? So there really isn't anything new contained in this. It's just more convenient for describing rotational motion. Okay. So in the case of this body executing uniform circular motion, so let's go back to this case where we had this body, and there's some force acting on this. Don't know what the force is. Don't really need to know what the force is. There's some force acting on this, oriented back towards the center of the circle. It could be a rope. It could be gravity. It could be anything. It could be a spring. Doesn't really matter. Let's calculate the torque from this. What is the torque present because of that force? Well, here's R, and there's the force. So what is the torque that's present in this case? Zero. Good. Yes, they're anti-parallel, so the cross product is 0. So this force can produce no torque on that body that's moving around the circle. And that's the reason why the angular momentum is a constant. So as long as there's no torque, the angular momentum is a constant. Okay, so let's see where this is going. I'm going to paint for you a big picture here for the chapter so you can see what it is we're doing. You kind of laid out the general idea here. We've got these concepts, these new ways of describing rotational motion. And let's go through a description of something. I'm going to consider various aspects of translation on one side of the page and rotation on the other. And there is an analogy, maybe a comparison, a relationship between things that we dealt with when we were dealing with translation. We're going to be dealing with something that's kind of analogous or corresponding or parallel in rotation. This is on page 339. Does anybody have his book? Pull it open to page 339. Share with your neighbors. I'd like everybody to kind of have an eye on this as we go down. This is towards the end of the chapter. I'm going to be going down this here on the board, so if you don't have one, that's fine. But if you have one, it might be helpful. Whoa!
Well, I had it.
Mr. Jackson's book is alive. On page 339, and so if you don't have one, reach down and have a look over somebody's shoulder. Okay, now when we were dealing with translation, how did we measure translation of a body?
How do we measure it?
Yeah, how do we measure the translation of a body? We measured it in some specific way. What's that?
How far it's traveling.
Yeah, exactly, a distance. So let's call it x. It's a distance. What is the corresponding measure for rotation? When we're dealing with rotation, how do we describe how far a body has rotated? An angle. Okay, now let's talk about the rate of translation. What is that?
Velocity.
Yeah, generally speaking, it's velocity. Now I'm writing this in one dimension, so we still have yet to generalize this to multiple dimensions. But we have a velocity, which is the time derivative of the position. Now the position could be uniform linear translation, it could be uniform linear acceleration, right? The velocity could be constant, it could be changing. At each instant there is a velocity for a body. How about with rotation? That's right. We take the time derivative of theta. How fast is theta changing? We'll call that omega. That's the angular velocity. By, as I said, kind of a corresponding analogy to linear translation, where we have a velocity. Now suppose the velocity is changing. What is the rate of change of velocity? How about with rotation?
Angular acceleration.
I'll call it alpha. Will be omega dot. If omega is changing, what does that mean about the body?
It's speeding up.
Could be slowing down, speeding up, it's spinning up. Yeah, there could be a torque that's present causing it to accelerate. Okay, you're anticipating what's coming here. So before we know the presence of torques, but we can just look at a body, we can tell whether it's increasing its rate of spin or decreasing its rate of spin. Something is changing rate of spin. So that would be the angular acceleration. Okay, so corresponding to this, we have corresponding to translation. If we see that something is moving, we discern that there's something that's causing it to move, which we called impetus, and the measure of that, the specific measure of that, for this case, we called momentum. And we have Puritans Law. Puritans Law is that there's a relationship between the cause and the effect. If P is the measure of the cause, V is the measure of the effect. M is what? Resistance. That's right. The resistance to the action of its impetus. Okay, so with that, there's this new thing, the mass. And when we were dealing with dimensional analysis, we had originally had a length here, and then we had time involved, and now we have mass. So we have three different things, M, L, and T, involved in the types. How about for rotation? What would correspond to the momentum? The angular momentum. And we just saw that we could write that as the moment of inertia times the angular velocity. You see the parallel? In place of m, we have the moment of inertia. The moment of inertia is like a resistance. But now this is not a new kind of resistance. This is not something that goes beyond mass. This is just mass, but it's expressed in terms of its distance from the origin, distance from the axis of rotation. Remember, the moment of inertia for this body, that one that was doing uniform circular motion, was mr squared. Okay, so it's not like it's something new. It's just a different way of describing that kind of motion, specifically rotational motion, which is more convenient for describing rotational motion. But it's still the same old angular. It's still the same old momentum and mass, just re-expressed in a way that's convenient for rotation. Okay, so now, I'm not going to call it a new law. I'm not going to say it's, I don't know who to name that one after anyway, but it doesn't have a new name because it's not really a new principle. It's simply a different way of analyzing the same principles. It's still momentum. It's still impetus. It's the cause of locomotion. In this case, for example, in the uniform circular motion, it's still momentum that's present here. And the impetus is still what causes it to move. But it has a constraint, namely the force, the rope or gravity or something that's keeping it moving in a circle rather than letting it go straight out. Something is acting on this to provide the force that's necessary to make it go and move in a circle. If that force is cut off, if the rope is cut or something, then it's going to move in a tangent just straight out from along P. Right? So there really isn't anything new about this, so I'm not going to give it a new name here. Okay, but now we notice that the angular momentum was constructed from R cross P. Remember that. Okay, now we had another measure of kinetic activity, which was the kinetic energy. And in terms of P, it's P squared over 2m, or in terms of M and V, it's 1/2 mv squared. Okay, now let's see. I'm trying to remember, did you actually calculate the kinetic energy of this in the uniform circular motion? Did you? Okay.
Use it in terms of...
Yeah, number 7. Good. Very good. Okay, in terms of that moment of inertia. So what was the kinetic energy for this bond?
Alpha.
So you could write it one of two ways, L squared over 2I, or 1/2
I know my Greek.
I omega squared. Either way. Again, in correspondence to the translation. So I is like an M, omega is like a V, L is like a P. You see the correspondence.
You can say I, but I can't say W.
That's I. Okay.
Yeah, I owed it last year, and I was like,
All right, now let's turn to Newton's second law. Once we understand that momentum is the cause, impetus is the cause of locomotion, and mass and momentum is the measure of that, and we want to describe changes in the momentum, and this was Newton's second law. dp dt is equal to the sum of forces present, right? Whatever forces are present, their force laws are going to be written on the right-hand side of this, and so we have then an equation of motion. Newton's second law, also called an equation of motion. It's a differential equation, and if we write it in terms of x, we could write it as x double dot mx double dot is sum of forces like that. Okay, same thing. Okay, now for rotational motion, what will we have?
we have torque.
Yes.
Changing,
L dot is the sum of torques. Okay. Now, there's some limitation to this, but this is going to be true as long as the axis of rotation doesn't change. So I'm not writing down specifically here. I'm going to write it down here in just a second. So the analog, so-called analog to Newton's law for rotational motion, could be I theta double dot equals sum of torques present on a body. Okay. So let's look at a case where the sum of forces is 0. What kind of motion results? There's no net force acting on the body in a given direction. Uniform linear translation. How about if we have sum of torques is equal to 0? What kind of motion will result?
uniform circular.
Yeah, uniform circular motion. Or if we have a potato that's spinning, then we would say it's just uniform rotation. Okay, now there's a caveat here I'm not bringing up yet. I'm going to bring it up here in a minute that we need to be aware of. There is not a perfect parallel between translation and rotation, and the difference here I'll talk about in just a minute. But it's pretty good. I mean, so far it feels pretty good down here. And so now suppose the sum of the forces is a constant. What kind of motion results? Ola? Uniform linear acceleration. What if the sum of torques was a constant?
Uniform circular motion.
Yeah, uniform circular acceleration. I guess, or rotational acceleration.
I just make it a good acronym.
Uniform rotational acceleration. I don't have a good acronym for it. URA.
I'm a what?
Uniform rotational acceleration. URA. Okay.
Makes me
All right. Now, what was the thing that we did after we described? Okay. We also did simple harmonic motion, and there is something like simple harmonic motion for a rotational case, and that's the pendulum. Pendulum is somewhat like a simple harmonic motion. The difference is you're going to be looking at the difference in the very next homework. So pendulum is not precisely a simple harmonic oscillator, and you'll see the difference when you get to it. Okay, but we could say we have simple harmonic oscillator, and there's something like a small angle pendulum. That means that the pendulum, the angle of the swing is small, in which case it's closer and closer to a simple harmonic oscillator. SAP.
Thank you. Small angle pendulums.
Small angle SAP. Is it small? That means that the angle of the swing is very small, much less than pi over 10 or something like that in radians.
So like if I was on a swing, would that be that?
No, you're getting if you're really getting up pretty high. If your angle is more than in that case pi over 4, then you're not really doing simple harmonic motion anymore. It's still pendulum, but it's not simple harmonic oscillator. You'll see when we get to that in the next homework. So hold on to that. You'll see what I'm getting at there. Okay. What else did we do when we were doing translational motion? We've got force. We've got Newton's law. What else did we do?
Free fall.
What's that?
Kinetic energy.
Kinetic energy. Right. We did that. Wrote that up there. What? And something that used the kinetic energy. The work energy theorem. So how about work? So an increment of work by a force acting over a displacement dW is equal to F dot dr. And for the special case that the force is a constant, and we could say that the work is F dot delta R, but that's a special case just for constant force. Doesn't even apply for the simple harmonic oscillator. So is there something like this? And then we said that change in work, in fact, results in that increment of work results in a change in the kinetic energy. That's the work energy theorem for a infinitesimal displacement, very small displacement, with any force or sum of forces acting. So each force could contribute to increasing or decreasing the kinetic energy, depending on whether it's in the direction of the displacement or opposite to it. So do we have something like that for rotational motion? So it involves torque and then a rotation, and now I have an angle with a vector on it. So what is meant by this? D theta is a vector. Its direction is the axis of rotation, just like omega was along the axis of rotation, and its magnitude is a small angle. So small rotation, tau dot d theta. Tau is also along the axis, as we'll investigate torque here some more in the next one. This torque is also along the axis of rotation, generally speaking. And so there is also work. And so we also have a work energy theorem for rotational motion. For conservative forces, where the work doesn't depend on the path taken, we can find a potential energy that depends on position. In the same way, for conservative forces, where the work doesn't depend on the path taken, depends only on the endpoints, we can write a potential energy as a function of angle. Okay. So there's a pretty good analogy all the way down. And your task in Chapter 8 is to explore each one of these little pieces. And for the most part, in the cases that we're going to consider, it's really that simple. But I'm about to give you the caveat where things go goofy, and I just want you to be aware of it. You're not really going to study any of these. I just want you to be aware that it happens. Okay? And you will study it more when you're juniors, and you get a little older, and you can handle it. Okay. So let's suppose we take a potato, and we're going to spin the potato. Yeah, that's the kind of potato my wife grows. It looks really weird like that. No. She grows pretty potatoes. Actually, she didn't grow any this year. Our garden flooded. What's that? What's that?
She watches the lectures.
You gotta compliment potatoes.
Okay, so let's suppose we spin a rigid body around some axis. We just pick an axis. Now, depending on what's going on, the angular momentum may or may not be along omega. It's possible that the angular momentum will turn out to be at some angle with respect to omega. In general, you cannot assume that L and omega are parallel to each other. In general, L is not parallel to omega. That's odd. And that's the part where things get interesting and a little bit complicated. But you know about this example. Let me give you one. Let's take a football. Nice rigid body, elongated along one axis and circular cross-section through the equator. Now let's spin that football. If we spin it along the long axis,
No, that's not a good drawing.
it doesn't have to be a perfect football. It just has to be something that has circular cross-section and be longer on one axis. So if we spin it around the axis, then in fact L is in fact parallel to omega. And so if in the absence of any torques, that football or object that's shaped like a football will just spin, because the angular momentum is constant. Not omega, but L is a constant. Now, if we were to spin that same object. Let's take it and spin it through an axis that goes through the equator, through the belly of the football. Let's spin it that way. Now the same thing happens. You spin it like that. The angular momentum will now be parallel to the angular velocity. L is a constant of the motion if there is no torque. And so omega is also a constant. It will also, the axis of rotation also does not change. However, you all know this by watching it on television, at least if you haven't thrown a few ducks like I have. Okay, what's going on here? What in the world?
What is the expression?
Okay.
It's not a spiral, so
What does that mean to throw a few ducks?
If you don't throw a spiral. If you don't spin the football around one of those axes that I just described, either along the long axis or short axis, if you spin it around some other funny axis, then the angular momentum is going to be not parallel to omega.
Because the weight distribution on each side is different.
Well, you'll see why. There's some subtlety here, and to do it right, you're going to wait for the junior level class. But what happens here is that the angular momentum is not parallel to omega. Now, the angular momentum, in the absence of a torque, the angular momentum is what is constant. But that means that if L is fixed, then and the body is rotating, the relationship between L and omega is changing. So that means the axis of rotation is changing. So it's spinning, but the axis of spinning is spinning, right? And that's why you get this funny thing they call a duck. It's a terrible pass, right? It's hard to catch. It doesn't fly as far.
When you catch it, it does make a good play.
It's an opportunity. That's right. Yeah. Okay, to make a hero out of your quarterback.
DB status.
Okay. Now, so that's the point here where things are subtle, and we're not going to do those subtle problems here. In this class, we're always going to pick an axis of rotation so that the angular momentum is parallel to the axis of rotation. We're only going to consider those simple cases. So if we spin a football, it's either going to be along the long axis or along a short axis. Now it turns out, you will prove a theorem when you get to the junior level, that there are always at least three. This is a theorem that you will prove in junior mechanics. There are always, for any shaped body, any rigid body, at least, yeah. I'm going to write it this way. There is always a set, at least one set, of three mutually perpendicular special axes. These special axes are called principal axes. Principal axes of rotation. It's really interesting that it doesn't matter what shaped body it is, there are always at least three of these principal axes. Where if you spin it along the principal axis, the angular momentum is along that same direction. It's kind of interesting.
So what would be the third one in the football?
Okay. You have the long one, and then you actually have a choice of lots of them inside the equator, right? So there's actually lots of choices, but you could pick any two that go through the equator. And so you'd have three.
Oh, so like flip it this way or flip it that way?
Yeah.
Oh, that's cheating.
No, it reflects on the symmetry of the football. The football has symmetry. It has a circular cross-section. It has a real symmetry that's present, and that shows up as being that there are lots of different axes within that go through the equator, which are these special axes.
So no matter how ridiculous the shape, there's always going to be at least three of them?
Exactly.
Yeah, so if I put my glasses
And they're going to be perpendicular to each other.
Okay.
Really, it's rather a surprising result. It's interesting that you can do that. Any rigid body that you can start spinning, there are always going to be at least three different axes that will be special axes in the sense that you spin it around that axis and the angular momentum is going to be parallel to the axis of rotation, and so the motion will be quite simple. It'll just spin.
So if you know the first one, you can pretty much find the other two based on if it's perpendicular to the
Be perpendicular. If you know one, it's got to be
So it's going to be somewhere like a plane like this,
It's going to be, well, it's going to be 2 in a plane, but you don't know more than that. Right? So with the football, because it's got a circular cross-section, there's a lot of, there are lots of axes that you could pick here. But suppose you had, you squash the football and don't allow it to come back to its normal shape. You squish it. So now all 3 axes are different, right? But there's still 3 special axes of rotation in that case. And in fact, it's present around any oddball object. That's what's really surprising. This is true for any rigid body. As long as it's rigid, there are 3 such axes. They're called the principal axes of rotation. So, and this result is used in the text. There are going to be 3 principal axes, and with each principal axis, there's a moment of inertia about that axis. So, any rigid body is described in principle by its 3 moments of inertia. For some bodies, like a sphere, all the moments are the same. Doesn't matter which axis you spin it around. For a sphere, the sphere is great. Basketball is great. You can spin it around any axis, and it's a principal axis. And the moments of inertia are the same no matter what axis you pick for the spinning of basketball. Football is different. One of them is different than the other 2. Pumpkin, the same way. You got one that's different than the other 2. If you have a body like you take a pumpkin and squish it so it's not circular cross-section, then you got 3 different principal axes, 3 different moments of inertia, and that's as complicated as it gets. No more than 3. It doesn't turn into 4, 5, or 6. 3. It's as big as it gets. Okay? It's really an interesting result. It's complicated enough, but it's really rather interesting and rather rich. So that's the way in which the parallel stops between translation and rotation. You see, this is where the 2 diverge. They're not strictly parallel and analogous. There's this funny thing about rotation that you could pick an axis and try to spin it around that, and it won't give you a nice spin. It'll give you a wobbly thing. Okay, and that's the way in which rotation and translation are not parallel or analogous to each other. There isn't anything analog to that in translational motion. Okay. Now, there's one more thing I want you to look at. Let's see. So, in relation to that, there's another table I want you to look at. It's on page 357. It's a table of moments of inertia. So depending on how, it's got a list of different bodies, different rigid bodies, cylinders and cylindrical shells and pencils and spheres and plates and other things. A mechanical engineering textbook would have a more complete list of these. And you can see each one of them has a moment of inertia associated with it, depending on where the axis is. So the first entry in the upper left-hand corner is a cylindrical shell. Does everybody see that one? So I'm going to try to draw that here. I'm not very good at these things, so there's a cylindrical shell. Not bad. Okay. Now, how many ways can I spin this cylindrical shell? Well, I could put a spin on it along its axis that goes through the, right down the center of the cylinder. So let's see, to make that, there we go. That makes it a little bit better, you can see then. Okay, so if I spun it like that, then the moment of inertia associated with that is just mr squared, where m is the total mass of the object and r is the radius. Well, that's a lot like what we derived for the single body moving in a circle, right? So you can imagine all the pieces of this rigid body are executing uniform circular motion, and so they all have a similar contribution to the moment of inertia. So the moment of inertia is just mr squared. Okay, but let's suppose we tried to spin that thing in the lower left-hand corner. What if we tried to spin that same object perpendicular to that axis? So we spin it through an axis going through the equator. The moment of inertia there is 1/2 mr squared. Okay? So the moment, and that's a special axis, it will spin just fine. And the moment of inertia for that kind of rotation is 1/2 of the moment of inertia for the kind that's spinning around the axis. Okay? So a lot of the problems involve finding out what's the appropriate moment of inertia for that particular kind of rotation. Depends on the axis and how it relates to the body. Okay, so that's kind of previewing what you're going to be seeing here in Chapter 8. You're going to be investigating the extent to which there's parallel between the translation and the rotation, and applying what you knew before to the new cases where we have rotation. And so this is a problem. Let me show you what you're going to be doing, what you're up against here. Let's go back to, everybody remember this problem? Put a mass on a ramp, have a pulley, hang another mass down here, M1, M2, and you were to look for the acceleration of this thing, but you were neglecting the mass of the pulley. Right? Now you're going to have, the pulley has mass and radius. So let's suppose that the pulley is a disk of mass m, radius r, and thickness h, but the thickness doesn't matter because it's spinning. What's the axis of rotation? Well, it's through the center of that disk, right? It's going to be spinning like this, right? The axis is along the axle. And looking at that table of moments of inertia, is there an associated moment of inertia for that problem, for that body? Does anybody see an entry in there which would work?
MR squared?
Yes, sir. Well, that's actually 1/2 mr squared. Imagine, take the upper right-hand example, the thick cylinder or ring about a central axis, and set R1 to 0. So then you've got a uniform disk. So it's 1/2. So the moment of inertia of this case would be 1/2 mr squared. So now, when these two masses start moving, they start accelerating.
How come it's the 1/2 MR squared?
Yeah, because it's uniform. It's solid. It's uniform disk, whereas this one we did earlier is hollow.
Oh, okay.
It's a shell.
Okay, that makes so much more sense.
If you think about it in terms of the distance involved, when all the mass is concentrated at this radius r, then each one of them is a distance r from the axis of rotation, and so the whole thing together, everybody has the same distance, r squared, and so altogether the total moment of inertia is mr squared. When it's a disk like this, some of the pieces are let me draw it better here. Some of the pieces actually have short distance from the origin, right? Or different distances from the origin. And so the net effect is 1/2 of what you get if you had a disk which was just a hollow disk. All the mass is concentrated on the edge. So a solid wheel is different than a wheel where all the mass is concentrated on the rim. That's a different moment of inertia. Okay. Now we look at this problem. When these masses, the gravity is pulling down on the first one, they start to accelerate. Now they have to turn that pulley. And it's got resistance in the form of a moment of inertia. So now, in addition to you could think of it in terms of forces. Let's diagram the forces on this just to show you where this is going. We have the force, the tension in the rope. We have the normal force. Let's don't put friction into this one yet. Let's just keep it simple. And then we have this other tension. Okay, but now we have the pulley, and we've got two tensions acting on the pulley, and they don't have to be the same. In fact, they're not going to be the same in general. Let's see why that is going to be. If we look at the torque produced by each one of these forces, one of them produces a torque. We're going to study torque more, but one of them produces a torque that wants to spin this body counterclockwise, and one force wants to spin the body clockwise, so they produce opposite torques. In order for the body to be accelerated in its rotation, it needs to have a net torque. That means there has to be a difference in those tensions in order for this thing to start accelerating. Okay? So T1 and T2 are not the same. Okay, so your homework will be, when you get to it, will be to find the acceleration of each body, the acceleration of the pulley, and the two tensions. And then, now what if we were to set the moment of inertia back to 0, we should recover the result that we got before, which was the massless pulley. Okay? So it just raises the stakes a little bit, makes it more realistic, introduces rotation into the problem. You're also going to do just the ball rolling, or bodies rolling down planes. Now we've got rolling finally. So now we've got the thing that can roll, it could slide, it could do something in between. So we've got finally something a little bit more realistic than just blocks sliding down planes. Now things can roll. Okay, so we're going to investigate all of these kinds of problems in this chapter. So your homework for Wednesday is to look at the pendulum. You're going to look at the pendulum problem. You're going to see in which way it's similar to the simple harmonic oscillator and in which way it's different. On the pulley. Yes, sir. There is friction present on the pulley, static friction, which does no work. Does no work. Static friction does not do work because there's no sliding.
Pendulum!
Wait, Darren, what? We have the chem test, but I doubt we have
They wouldn't be that legal.
What?
I don't know.
No, yeah, it's on November 18th.
I would never under.
Huh? Whatever. It's like November something. I don't even know if we have a test still. We have to go into the test.
That's really the only reason I asked is that I don't have any class on Tuesday except for 7 to 10 p.m. physics lab. So Thursday is then just to go to the lab.
That would not be worth it.
I would not be able to go on. I need my son's lab.
No, they would. It's not enough of us in the game.
No, I mean, like,
If none of us showed up for Mr. Gall's class, I'm sure you'd just mark us all absent and go home. Or you might still teach, it's recorded.
If nobody showed up for class,
on the Monday of the week of Thanksgiving,
I would think, what did I do wrong?
we would watch your recording at home.
While you take another nap? Having eaten too much?
After I recover from my turkey sandwich.
Yeah, that's right. Having eaten too much turkey.
So, the same Jews,